It's loading. Yes, so we are live now.
Excellent.
Hello, everyone. Welcome to PF Talks, episode 2. For this episode, we have a very special guest, a physicist who conducts research at Fermi National Accelerator Laboratory, a PhD in experimental particle physics. He has co-authored more than 1,000 scientific research papers. He was the co-discoverer of the top quark and was the member of the team which discovered the Higgs boson back in 2012, and the host of Fermilab, which has around 4.5 lakh subscribers. He is Don Lincoln from Chicago, United States. We welcome you to our show, sir. Now, my teammate Pawan will be starting off this session with few quick questions.
How are you, sir?
Oh, very good. And you?
Fine, sir. Thank you for sharing some of your valuable time, sir. What do you think is the best thing about physics?
What do I think is the best thing about physics? I'm just making sure because there's a little bit of crackle in your connection. Okay, so what do I think is the best thing about physics? The physics, well, it actually depends. Different people have different interests in physics. Some people want to, well, in general, we want to understand the rules of the world. Now, some people want to understand practical things, like they want to figure out how computer chips work or make changes to technology, things that allow us, give humans power over the world. But then there are a class of physics people who are interested in very deep and fundamental questions. So these are particle physics and cosmologists. And this is as close to religion you can get, because you can ask and answer questions that were once in the realm of religion or philosophy. We can ask questions like, how did the universe come into existence? We can ask questions like, why the rules of the universe are the way they are. And while we don't have final answers, and nobody should think we do, we are learning about some of the oldest questions ever asked by mankind. And that's why I like physics.
Right, sir. Do you think physics can help in changing the future with some exciting new technologies like quantum computing or interstellar travel, etc.?
I actually have to apologize. Are other people getting crackle on his connection? Because it's very hard for me to understand.
I will say, sir.
Oh, I hear you much better.
Do you think physics can help in changing the future with some exciting new technologies like quantum computing or interstellar travel?
Physics will absolutely help the future, without a doubt. In the past, simple things like understanding how electricity moved through crystals, through things called semiconductors, eventually taught us how to invent transistors. And once transistors existed, computers came into existence, and we are now able to talk to each other. You are 12,000 miles, so you are like 18,000 kilometers away from me, and we can talk to one another. And that is one of the things that physics has done in the past. Now, going forward in the future, physics will come up with additional things that we don't understand now. Now, will quantum computing become important? That's a very hard question. And in principle, I mean, theoretically, people understand how quantum computing could make very powerful computers that will make things like ciphers that are unbreakable, and will also be able to break current ciphers very, very quickly. It will completely change how nations speak with one another. On the other hand, we're not entirely sure that quantum computing will ever rise to the promise that people hope it will have. It's technically a very, very difficult thing to do. I expect we'll overcome the technical problems eventually, but it may be that there are other forms of computing that are as powerful once we've solved the quantum computing questions. So it's hard to know about that. As far as interstellar travel is concerned, you know, gosh, I would absolutely love if that were to be true. I mean, this is something that I would like to explore the galaxy. However, what will have to happen is one of two things. We will either have to accept the fact that we will explore the galaxy going from star to star at speeds lower than light. And if we do that, it's going to take us a very, very long to traverse the universe. Now, this is technically possible. It will be very difficult. There's a lot of engineering concerns that we will have to solve to do that. But it's at least reasonable. For something like you see in Star Trek or Star Wars, where people are able to go from star to star in a day or two, that will require that we invent an entirely new kind of physics. And the universe is not required to do what we want. It may be that such a thing is possible. It may not. I mean, nobody can make this prediction. We can only hope and search. So, you know, if I had my choice, if the universe asked me what I wanted, I would say yes, we will figure out interstellar travel. But the reality is, for the foreseeable future, we might do it the old way, and which means it's going to take a long time to explore space.
Yes, sir. What is the weirdest topic which you have learned in physics?
What is the weirdest topic I've learned in physics? It's hard to say. I mean, quantum mechanics is awfully weird. The fact that at the very smallest level, things don't seem to follow cause and effect in the same way that they do at the level that we're familiar with. I mean, at the level we're familiar with, you drop a glass and the glass will fall. At the quantum level, that's not necessarily true. If you drop a glass, it is likely that it will fall, but maybe it won't. So I think quantum mechanics is the weirdest thing. Relativity, especially special relativity, is also extremely weird. The fact that clocks seem to, the rate at which clocks tick depend on your velocity is really a crazy thing. But at least for me, I've been able to sort of get my head around relativity, so it doesn't seem weird to me anymore. But quantum mechanics seems weird to me, even after 3 decades of learning about this sort of stuff. It still seems a lot like magic.
How does quantum mechanics differ from classical mechanics?
So in the world of classical mechanics, we have a great familiarity, especially for those of you who have taken physics. We learn about velocity and acceleration and position and energy and momentum. And if you know the condition that a situation, that a thing exists in, since you have a ball, you know its position, you know the forces that surround it, you know all of this thing, you know its initial velocity, you can predict with very good accuracy what will happen at all times in the future. So this sort of physics began, well, in the very far past, but perhaps became of age with Sir Isaac Newton back in the late 1670s. That was when we began to understand the deterministic laws of the classical universe. And from that, we have been able to do an amazing amount of things. We can shoot rockets into space and go to Pluto, which is an incredible distance away, and we can go to where we want to with incredible accuracy. But in the world of quantum physics, none of that is true. In the world of quantum physics, it appears that the universe is governed by probability. Now, I say appears because the simple fact is we don't understand, no scientists understand quantum mechanics in great detail. We understand the mathematics of quantum mechanics extremely well. We understand how we can generate an equation and make a prediction about what will happen. And we will talk about this, I'm sure, in a little bit. But in quantum mechanics, we have this thing called a wave function. And the wave function is intrinsic to quantum mechanics. And it's the mathematical description of the quantum world. The problem is nobody knows what the wave function really is. If you believe in certain interpretations, you will say the wave function is the probability that something will happen, or technically if you square the wave function, it's the probability something will happen. If you, other people think of the wave function as something that it's a similar thing, but it describes everything. For instance, will you go to the right or will you go to the left? Both of those things can occur, and you do one or the other. But the wave function is actually both. And the experience that you have in life is you following this tree of branches where you go and you do this and you do that and you do the other thing. So that's a sort of complicated mixture of things. But at the very fundamental level, quantum mechanics describes what happens at the very, very small scale, and it seems to be probabilistic, whereas classical physics governs big things and seems to be deterministic.
What is the significance of Schrodinger's equation? What does it try to explain?
Okay, so Schrodinger's equation is fascinating. It was invented in 1925 by Erwin Schrodinger, and it arose from some earlier work by Louis de Broglie. And what de Broglie found was or postulated, I should say, he didn't actually find it, was that matter was both a particle and a wave. And the reason he postulated that is we learned early on that photons have both particle and wave properties, and he's just simply postulated that this was true of matter as well. So Schrodinger said, well, if matter is a wave, then there's an equation that has wave properties that governs matter. And so what he did is he generated this complex equation which uses differential equations, which is like calculus, but a little bit more complicated. And what it does is he takes the wave, not the wave equation, the wave function. And the wave function is what says where the probability you will find particles in certain places. And the Schrodinger equation says how the wave function will change. And so what that means is if the wave function tells you where things are, then Schrodinger's equation tells you how the wave function changes, and therefore it tells you where you will find things in different locations at different times. So that's kind of mathematically what it is. At a very simple level, it's kind of interesting because the Schrodinger equation bridges the classical world and the quantum world, because in the Schrodinger equation, it's not probabilistic. It tells you how the wave function changes over time, and it's completely deterministic. But and it's only when you actually make a measurement that probability comes into play. So I think the important thing is simply you have to remember at the micro scale, the quantum scale, the wave function tells you the probability you will find things, and the Schrodinger equation tells you how that changes over time. So it's effectively telling you how things move. And that's what it does. It's very fascinating. It's very complicated. And you can learn the basics relatively early in your university career, but you could spend a career trying to make predictions.
Quantum superposition says that a particle can be at two places at a single instant. How can this happen?
So quantum superposition is actually a little bit different than saying a particle can be two places at a single instant. Quantum superposition says that a particle can be in two what they call states at the same time. Now, this is a very tricky thing to do without drawing pictures. But suppose you had a wave function that says that a particle can be anywhere inside a square. So it doesn't tell you where it will be, but it tells you the probability that you will find it in that square at different locations. So that is a single thing. And that means in that particular case, there is the wave function is this square shape, and the particle can be anywhere inside that square. So that means it can be in two places. It can be in this corner or it can be in this corner. that is intrinsic to quantum mechanics. But quantum superposition is even more complicated because it says that the uh, particle can be in two different wave functions. So there may be one wave function, which is a square, and another wave function, which is a circle. And quantum superposition says that it can be in both of those states. Now, in a circle state, it tells you the location of the particles anywhere in the circle. So even if you know it's in the circle state, you don't know where it is. You just know it's somewhere in the circle. If it's in the square state, you don't know where the particle is. It's somewhere in the square. But quantum superposition says it's even weirder than that, because the particle can be both in the square state and the circle state at the same time. Now, we don't actually use circle states and square states. What we do is we usually use energy levels. And so that says that, for instance, a particle can have a certain energy or a second energy. And even if it just has the first energy, it can be many locations. If it's in the second energy, it can be in many locations. So quantum superposition says two things. It says it can be in two energies, and with each energy, it can be in many locations. So it's even more complicated than just being in two places at one time. And that's the simplest quantum superposition. There are other quantum superpositions that can say it can be in multiple spin states, it can be in multiple locations and energies. It can have multiple velocities. So it can be very, very complicated.
How can we prove the Heisenberg's uncertainty principle?
Well, that one's tricky. So the Heisenberg uncertainty principle says that a particle can have, you cannot simultaneously measure the position of a particle and its energy with good precision. And if you dig deep down into the Heisenberg uncertainty principle, you find out that it's buried in the mathematics, and it's buried in the fact that all particles can be described as a wave. So if you dig down into the wave mathematics, it says that you can't find the location of a particle very accurately unless you don't know the wavelength of the particle. So if the wavelength gets big, the position can be small, or our knowledge of the wavelength gets big, the position can be small, and vice versa. So that's what it is, and it's a little different than most people think of it to be. Proving the Heisenberg uncertainty principle is a little trickier, and you can do it in sort of simple ways. You can try to take an electron and you can put it in essentially a box. Now, this isn't really a box. There's maybe two electric fields, and you make the electric fields closer and closer and closer together. And as you put them closer and closer together, you can measure the speed that the particle has inside the box. And what you find out is, as you make the box smaller and smaller, the measurement of the velocity varies very much. Whereas if you have the box far apart and you measure the velocity, you find out that the velocity is maybe one velocity, or a velocity with a very small uncertainty. But as you close the box together, you find out that all the various velocities that can be in for that particle get bigger and bigger. So that's kind of technically how you do it. It's actually kind of interesting. For instance, one of the things that we learned about when we understood what's called quantum chromodynamics. So this is the theory of the strong forces, the theory that governs what protons are. And so protons have a specific size, and the size is 10 to the minus 15 meters. So it's very small. It's a femtometer. And because the size of the proton is a femtometer, if it has that size, then it's a very, very small location. You know exactly where it is. But because you know exactly where it is, you don't know its energy very well. And the mass of a proton is, if you use Heisenberg uncertainty principle, you can see that if anything that has that small size must have the 1 billion electron volt energy that the proton has. And so that's really kind of a like a neat little thing that had nothing to do with taking an electron and putting it in a box, but you can take something using another physics, in this case the strong force, and you find that something that is in such a tiny box has to have the mass that it does. And it works out that it has exactly the mass that you'd expect from Heisenberg. So it's these kind of things that you can do to use to figure out Heisenberg.
What is the best known explanation for wave collapse? For collapse in a wave function?
Best is a very difficult question because we really don't know what happens when a wave function collapses. So let me share a story with you. So you guys are all young, and believe it or not, I was young once too. And when I was young, the thing that completely confused me was the collapse of the wave function. Now this was perhaps 40 years ago when I was close to your age, and I didn't understand it. Now that seems like a long time, but people have not understood the collapse of the wave function since 26 or 27, something like that. So we are now talking about 100 years where we have known about the collapse of the wave function, but we don't really understand what it means. So I will tell you a few explanations, but of course the reality is that nobody knows, and I wish we did. If any of you guys figure this out, you'll get a Nobel Prize. You will be considered the new Einstein. You will be brilliant. And so it is a very hard question you just asked. So in a interpretation called the Copenhagen interpretation, what happens is you have the wave function, and the wave function is it's just a function, and it's spread out. And that says that the particle can be in all of those locations at once. And when you make a measurement, what happens is the wave function goes from being spread out to being in a single location. And that's where the name comes from. It's called, the wave function goes from the spread out thing to a single thing. And so that's why they called it the collapse. And that's the language, and this is the language of the Copenhagen interpretation, which was worked out by Bohr and Heisenberg nearly 100 years ago. But people have not been really happy with that idea because it just seems like magic. And so later in I guess it was the 1950s or early 1960s, Hugh Everett came up with an idea that says that the wave function doesn't actually collapse at all. What he said is that the wave function is sort of like a tree with all sorts of branches. And what's happening is as a particle changes in time, it evolves. And so if it comes to a place where the particle can go right or left, both of those things exist, and the wave function collapses when the particle chooses to go right or left, and that is a probabilistic thing. But in that case, there is no collapse of the wave function. The particle is just moving along the branches, and it just picks a branch. So that's sort of an interpretation of the collapse of the wave function. There is a final thing, that what we call pilot wave theory, which just says that it's basically like old Newtonian physics, but the particle is like a surfer on a wave, and the wave is just telling the particle where to go. And in that case, there is no collapse of the wave function. We're just determining where the particle is at that time. And so these are three explanations, and there are more possible ones, and all of them are attempts to figure out what the collapse is. Now, we're pretty sure that the pilot wave theory is wrong. And I admit that I kind of wish it wasn't, because that's the one I would like to be true. It's the one that seems the most sensible to me. But experiment says that that's false. And the one that I sort of live with is the Copenhagen interpretation, not because I like it, not because it's satisfying to me, but because it makes good predictions. And the good predictions have allowed us to make things like transistors and lasers and all sorts of things. So, best is a very hard thing, which is what you asked about. And I'm not sure there is a best. I just know that the Copenhagen one has been effective in generating technology. But it's very unsatisfying intellectually, and I don't like it at all. And personally, I think that I hope that someone will come up with a better explanation.
Every force has a carrier, like electromagnetism has photon, strong force has W and Z boson. The force of gravity is said to be carried by graviton. If we believe in general relativity, which states that gravity is not a force but distortion of space-time, then why do we even think of graviton, which carries the force of gravity?
So that's a good question. So let me first correct one thing. The strong force does not have the W and Z bosons. The strong force has the gluon. That is the force carrying particle of the strong force. The W and Z boson is the force carrying particle of the weak force. So that doesn't actually change your question very much, but I thought I would just mention that. So you are absolutely correct. General relativity talks about gravity as being the bending of space and time, and that particles travel straight lines in bent space. That is what it says. So I'm going to tell you a deep and dark secret, and I hope you won't share it with anybody, but just between us. General relativity is wrong. And we know general relativity is wrong. Now, that doesn't mean that general relativity is stupid. General relativity makes fantastic predictions. It makes predictions of how Mercury orbits the sun that without general relativity, it makes the wrong predictions. It predicts black holes. It predicts that gravity or gravitational waves exist, and we have measured them recently coming from the merging of black holes. Most importantly, and this is one of the most fascinating measurements I've ever heard of, we have very precise atomic clocks. And if you take the two atomic clocks that measure things to parts per quadrillion, so very, very precise, and you take the two clocks and you lift one clock up by 30 centimeters, the two clocks will tick at different rates because of the different gravity here on the surface of the Earth. So general relativity is amazing. It is wonderful, it's true, but it's incomplete. Because if you take general relativity and you try to apply it in the world of the very, very small, it predicts infinities. And if a theory predicts infinities, it's wrong. So there's a lot of examples of things like this. For instance, Newton's law of gravity works very, very well. We can make satellites orbit the Earth. We can go to the moon. We can shoot probes to Mars with with great accuracy. But if you want to measure things very precisely, like what happens in very strong magnetic fields, it's simply wrong. So general relativity is the same way. It works very well on the big scale. It's a wonderful theory, and you should believe it. But you should know that all theories are eventually wrong. So with that said, we must invent a theory of quantum gravity. Now, what does quantum gravity look like? Well, we actually have no idea. We've been trying to think about quantum gravity since quantum mechanics was invented. Albert Einstein spent the last half of his life trying to understand the theory of quantum gravity, and he failed. But why do we think that gravity should be a force and there be a graviton? Well, basically, it's because all forces are like that, the other forces. What we know is that when we took the other forces, whether it be electromagnetism or the strong force or the weak force, and we looked at on very, very small scales, the way we generalize them is we said that the particles have fields, and if they have fields, they are quantized, and if they're quantized, they have wave functions, and these wave functions generate particles that carry the force. And so we are taking our knowledge, our successful knowledge of what we did with these other theories, and we're saying, well, if we do the same thing to gravity, then we'll follow the same approach. So there will be a field, and there will be quantization, and the outcome there will be a gravity particle, and the particle is called a graviton. So the thing about that is then you have to say, take whatever the quantum theory of gravity is, and you have to extend it to the big world. And but that's not new. That's true of even quantum mechanics. The world of atoms gives weird predictions, but when you look at what happens when you throw a soccer ball, we know what happens. So we're going to have to do the same thing with quantum gravity. So we will have these individual gravitons jumping back and forth, causing a force. But when you look at it, and you look at it from a long ways away, that will have the same structure as the bending of space that general relativity has. So that's a long explanation or a long statement. But the problem is we don't know a theory of quantum gravity. It doesn't exist. The closest thing we have are it's called the superstrings and loop quantum gravity. And neither of those have been proven to be true. And people are continuing trying to understand it. So to make a long story short, we believe that there's a graviton probably because when we made the other forces quantized, there was a force carrying particle. And hopefully we will find one in graviton, the graviton. But maybe we won't. You should not, nobody should believe in a graviton. That's rule number one. You should not believe in it. It's just a plausible idea and it makes sense and it might even be right.
Do you think extra dimensions exist?
Well, extra dimensions are tricky. So when people talk about extra dimensions, they often misunderstand what they mean. They think about extra dimensions as like parallel universes, like you can jump from a universe where where you are a student in your school, but in another universe you are prince of your country, and you can be in both universes. And that's not what people really mean, or not what physicists mean by extra dimensions. What physicists mean by extra dimensions is they mean extra physical dimensions. So we're familiar with the 3 dimensions of space. So you can go left and right, forward and backward, and up and down. And those are the 3 dimensions of which we're aware. Scientists think that perhaps there are additional extra dimensions, but those dimensions cannot be like the ordinary dimensions because we know very well that there are 3 dimensions. But it's possible that there are very, very small dimensions. Now, this is very hard to understand, but imagine that at every space in time, every point in space, there is a little microscopic that you can't see it ring. Now, this ring, if you're on a ring, you can go anywhere around the circle of the ring. And so even though and now this ring is really, really tiny, so you can't see, if you're just looking, it looks, no matter where you are on the ring, it looks like it's in the same place. But there may be these extra tiny, tiny dimensions where in addition to X, Y, Z, you have a location around the ring. And there could be more extra dimensions. It maybe isn't a ring, maybe it's a sphere. And so on a sphere, to find the location on a sphere, you have to have 2 locations. And so if that was true, if every point in space has an extra sphere, then you would need the 3 dimensions to find out where the sphere is, and you would need 2 extra locations to find where you are on the sphere. And there can be more and more. And in fact, in a certain theory called superstrings, there are supposedly a total of 11 dimensions, of which 1 is time, 10 are space. We have the 3 that we know of. So they think that there are 7 additional dimensions. So you have a very complicated little object, tiny object. So that's what we mean by extra dimensions. And the reason that we think that there might be extra dimensions is that one very interesting idea, was very popular about 10 or 15 years ago, is there was an explanation by Lisa Randall and her collaborator, Randall Sundrum, or rather Raman Sundrum. And what they came up with is they thought that the reason that gravity seems to be much weaker than the other forces is maybe gravity can go into these extra dimensions. And so it just means that gravity has more places to spread out than the other forces. And so that's a really neat idea. I really like it. I don't believe it, but I really like it because it's fascinating. It's clever. The people who invented it are very smart. Now, we have tested this theory. We've actually said, are there extra dimensions? And you can do that by colliding beams of particles together, and you generate a lot of energy. And if the energy is in a very small location, then that energy might be able to at least investigate these small dimensions. So we've done this experiment. I have not personally, but my group has done that experiment, and we've published papers on that. And we find exactly 0 evidence that extra dimensions exist. Now, when I say we found 0 evidence, that doesn't mean that we know extra dimensions don't exist. It just means that we didn't find them. So what we've done is we've ruled out some ideas about extra dimensions. Extra dimensions could exist. Do I personally think extra dimensions exist? Probably not, but that's an opinion, and it's only an opinion. You should not take it as anything more than an opinion. All I'm willing to say as a scientist is that we've ruled out some ideas, other ideas remain possible. But if you wanted me to bet, if you were going to offer me a bet, I would bet against it.
Now, Trilok will be asking the questions commented by our audience.
Okay.
Here are the best questions asked by our audience. First question is, what is a wave questions and wave function? And it is from Indian Game Award.
What is a wave function? So as I've said earlier, we don't really know what a wave function is. A wave function, it's a mathematical thing. And you can draw a picture. It could be a sine wave. It could be like a bell curve, goes up and comes down. It could be many things. And what we know for a fact is if you take the wave function and you square it, then that will give you the probability of finding a particle in a certain location. And that we know, we've been measuring that for nearly 100 years. So that's a fact that the wave function squared will give you the probability. But what is the wave function itself? And the short answer is really nobody knows. It's a complete mystery, and you will find many opinions from many scientists, but there will be opinions. The fact is we're all very, very puzzled. In fact, if you're not puzzled by quantum mechanics, and if you're not puzzled by the wave function, then you haven't been listening, because it is very puzzling. I think you're muted.
Why are the universal constants the way they are? Why couldn't they differ? The question is from Physics in Essence.
So why are the what the way they are? The fundamental
The
constants?
universal constants, yes, sir.
Again, it is very easy for you guys to ask questions that I don't know the answer to. I've been studying this for, a long time, much longer than you've been alive. And people have been studying these questions before I was alive. Nobody knows why the fundamental constants have the reasons, have the values that they do. And that is a really very big mystery. So there's a couple of possibilities. One, it may be that it is literally logically inconsistent to have a universe with different fundamental constants. But that doesn't make any sense really to anybody, because you could imagine changing the speed of light, or you could imagine changing the mass of an electron, and there would be a different universe, and it would have different physical properties. So some people came up with this idea of the multiverse, which is a very maybe not a crazy idea, but a very adventurous idea. And that says that there's not one universe, there are many universes. Every universe has a different set of physical properties. And so then you would ask, well, why do we live in the universe that we do with our physical properties of those constants? And the answer is, well, we have to live in a universe where the constants allow for complex matter to exist, because if complex matter doesn't exist, we don't exist and we can't ask the questions. So that is the multiverse answer to that. I'm not a super fan of multiverse, although many physicists think the multiverse is a very strong idea. It could be true, but getting back to the honest answer to your question, nobody really knows why the laws of physics and the values of the fundamental constants are what they are. These are mysteries. We will need a theory of everything to explain that. And I'm confident in saying that it will be thousands of years before we can answer your question. So it's an excellent question. I just wish I had a better answer.
The next question is everything in the universe random? And the question is asked by MK Arts.
Is everything in the universe random? Well, that comes down to what you think about quantum mechanics. Certainly at the quantum level, if you treat the wave function as a probability, then at the quantum level, everything does appear random. But as you take more and more particles and you bring them together, randomness becomes a little less random. Now that is a weird thing, but we're at least kind of used to that even in the classical world of physics. For instance, in the room in which you are now, there are molecules of air that are floating around and they move in random directions. And so if you looked at any individual molecule, it could go this way or that way, it would bounce into things and it would move around randomly. But when you take not just one molecule, but 2, 3, 4 millions, billions, Avogadro's number of them, then you can make very accurate predictions about what will happen in the future. And we indeed know this in our room. We know what the air pressure is. We know that if we wave our hand, there'll be a slight breeze, and we can make predictions. So the answer to the question is yes and no. It seems at the quantum scale, things are random, but when you take large accumulations of randomness together, they can make a deterministic prediction. So that's the short answer. So it's an unsatisfying answer, but I think it's the true one.
The next question is, do you think graviton can be detected? And it is from Roblox Gamer.
Try that, please, again.
Sir, do you think the gravitons can be detected?
Oh, do I think gravitons can be detected? So that is a question I think I can answer actually more definitively. So gravitons, of course, are the force of gravity, or not the force, the particle of gravity. And we know that gravity, because we can do very simply, we know that gravity is much, much, much weaker than, for instance, electromagnetism. We know that, depending on some details, gravity is perhaps a 10 with 40 zeros, 40 zeros times weaker than electricity. And so if that's true, and it appears to be true, then I think we will never, or at least not in your great-great-great-grandchildren's lifetime, be able to make a graviton detector, because gravity is so much weaker that a single electron or a single proton or a single whatever emits gravitons very much less than it emits photons for electromagnetism. And so trying to find a graviton in that is like trying to hear a whisper in a rock concert. So that's totally impossible. However, and I have to say however, you asked earlier, or someone asked earlier, about extra dimensions. If extra dimensions exist, and that is the reason that gravity is weaker than the other forces, then we have a different situation, because gravitons still have zero mass and they're very weak. But if gravitons can get into the extra dimensions and circle around it, like going around a ring or going around the surface of the Earth, then they could have a lot of energy, but it would look like they weren't moving as far as we're concerned, because they would be in one place moving in these extra dimensions. So if you have a lot of energy and no motion, the only way you can have that is mass. And so if extra dimensions exist, then gravitons will look like they have mass, even though they don't. And the only reason they will look like they have mass is because they're locked in these small dimensions. So it is possible, if extra dimensions exist, that what we will find is we will find massive gravitons. And if we find massive gravitons, then first we'll have proved that large extra dimensions exist. Or by large, I mean they're still smaller than an atom. And also, the way we will probably detect it is by making a microscopic black hole, a tiny, tiny black hole smaller than an atom. And that will be another indication that extra dimensions exist. So that's the only way I think we'll find gravitons. If extra dimensions exist, that it is possible that we will find a graviton, but only that way.
Thank you for answering our audience's curious questions, but we have received even more. The next questions will be asked by Sriram.
Hello, sir.
Sir.
Here are some more good questions asked by our viewers. The question from Pavan is, can quantum computing help in solving complex calculations?
So yes, in principle, quantum computing can do some very complex things, especially cracking codes. That's one thing that quantum computing that we're pretty sure will work. The problem is the technical achievement of making a quantum computer, because what you have to do is you have to put a particle in a certain quantum state, and it has to stay there for a long time, or a long time can be a second or 2 seconds or 3 seconds. For instance, at my laboratory, Fermilab in the US, we have just recently received a large grant from our government to make a quantum institute for studying just precisely that. And whether or not it will be possible to solve the technical problems to make quantum computers is still unclear. It might just be that it's too hard to make quantum computers. However, if quantum computing does is achieved technically, then it will be able to do some calculations in fractions of a second that it would take a normal computer thousands or millions of years. So yes, so the answer to your question is yes, but yes if. And the if is if we're able to make one. And that's still unclear to me.
The question is from Ram. What do you mean by color in quantum mechanics?
What do I mean by color in quantum mechanics?
Yes, sir.
Okay, so color in quantum mechanics. All right, let's back up. So quantum mechanics is a big term, and it is the study of the world that's very small. Now, that's a very vague term, but for individual forces, there are different theories of quantum mechanics. For instance, for the theory of electric charge, there's quantum electrodynamics. So that's the quantum mechanical theory of electricity. There is the weak force, and we just call it weak theory. It's not a very smart name. And that is the quantum mechanical theory of the weak force. There's also the strong force. And the name for the quantum mechanical theory of the strong force is quantum chromodynamics, which is a very long name. And so that word chromo is where the word color comes from. So in electricity, you have two kinds of charges. You have the plus charge and you have the minus charge. And if you take a plus and a minus and you add them together, what happens is you get zero. In the strong force, there's not two charges, but there are three charges. And so that's a very weird thing. You have to add charge 1 plus charge 2 plus charge 3, and that equals 0, instead of with electricity, which you have charge 1 and charge 2 equals 0. So historically, we've seen this thing, and by I mean historically, I mean hundreds of years ago. We were familiar with the idea if you take a red light, a blue light, and a green light, and you shine them on the wall together, the place where all three lights are shining on the wall looks white. And so we might say, as a metaphor, that white is no color at all. And this is worth doing. So if you can do this, get a red light, a blue light, and a green light, shine it on a wall, or you can Google this and see it. It's just amazing. It doesn't sound like it should be true. If you mix those colors, you'd expect that it would be some weird mixture of red, blue, and green. It would be an ugly color. Like if you mix red, blue, and green paint, it's an ugly color. But red, blue, and green light shining on a white wall looks white. It's amazing. So when it became clear that with the strong force that there were three distinct charges, one of the individuals that invented the strong force said, you know, if we have these three charges equals a neutral particle, well, that's very similar to having the three colors equaling white light. And so what they did is they said, okay, we will just call these three strong charges color. And we name them red, blue, and green. Now, they have absolutely nothing to do with red, blue, and green. It's actually kind of dumb and a little confusing. But that's what we mean by that when we talk about color in quantum mechanics. What we mean is it is the charge of the strong force, and it's from that metaphor of color, of real, honest to God color that you see with your eyes. So So it's confusing. So just think of color as the charges of the strong force. That's what we mean by that.
The question is from Alikya. What is Zeeman effect?
Okay, what is the Zeeman effect? The Zeeman effect is a simple thing. Whoops, hold on. I'm answering a question. Okay, sorry. The Zeeman effect is when you take a magnetic field and you put it on an atom, it will change the energy of the atom. So we need to back up. So in a simple atom, there are different energy levels, and you can think of the energy levels as maybe like rungs on a ladder. You have the bottom one and the second one and the third one. And so there is a certain amount of energy difference between the bottom rung and the second rung, and another energy difference between the bottom rung and the third rung, and so forth. Now, if you have no magnetic field applied to the ladder, then what will happen is when an electron jumps from one rung to the next rung, it will emit a photon of a certain energy. So that's just how it works. Now, if you apply a magnetic field to the atom, it will actually essentially change the locations of the rungs of the ladder. So there will be a different distance between the rungs than there was without the magnetic field. And so if there are different distances between the rungs, when an electron jumps from one to the other, the photons that come out will be of a different energy. And so what you see when you look, when you just do a measurement, is you take a gas, you heat it up so that it's glowing, you put a spectrometer on it, and you see what color lights are coming out. There will be distinct colors. You put a magnetic field on it, and each one of those lines where you have a certain color, it will break up into a couple of colors because it will be changing the distance between the rungs on the ladder, or it will be changing the energy of the energy levels in the atom. And so that's what the Zeeman effect is. Now, one thing that is really, really fascinating about this, because we can do this in the laboratory, and in doing so, we can we can prove that this is true. But now, if you look at light coming out of a star, say our sun or some other thing, and you know what, for instance, light that hydrogen gives off, but if you look at the star and you see where those energy levels should be, if you see a couple of extra lines, you see them starting to spread out, then you know that there is a strong magnetic field on the sun. And so this is a fascinating way where you can look at a distant star 10 light years away, 20 light years away, and by looking at the spectrum of light, you know something about the magnetism of the star because the Zeeman effect splits these energy levels and makes different color light. So that's an absolutely fascinating thing that we can do to help us understand magnetism in astronomy.
The last question is from Quizmaster. How useful are Feynman effect? Feynman effect.
How useful are Feynman what?
It was Feynman diagrams.
Oh, how useful. Feynman diagrams are fascinating. They are very complicated, very tricky, and very hard. So if you've ever seen a picture, I mean, you've asked the question, so you know what Feynman diagrams are. It looks like you have two particles, they come in and they make a photon that goes and it splits into another particle. Now, you might not realize that, but the Feynman diagrams are actually an equation that's hidden. And I wish I had pictures, I could show this to you. But the line coming in equals a piece of an equation. Another line coming in is another kind of equation. So if you see those two lines, you can start writing your equation. You can say this line is one term, this line is another term, the wiggly line is another term, and then the outgoing lines are two more terms. And so you do that, and you look at the Feynman diagram, just a simple cartoon, and you can easily convert that Feynman diagram into an equation. Now, if you have a more complicated Feynman diagram where you have two particles coming in and then a wiggly line, and then the wiggly line splits into two particles that go back together and makes another wiggly line, that's just a different equation. And so if you know how to take a Feynman diagram, what you do is you can then simply write the equation, the mathematical equation. Now that mathematical equation is usually incredibly difficult. Solving it is not something that you do even at the university level. If you go to university to study physics, you probably will not do Feynman diagram physics. You have to go to graduate school, and then maybe you will study that because it's very hard. But, and this is the neat thing, if you take that equation, will eventually give you the wave function, and if you square the equation, then that will tell you the probability that something happens. So the Feynman diagram is lovely because it's an intuitive way of writing down the wave function. I mean, eventually with a lot of math in between. So Feynman diagrams are absolutely fascinating. Now, one thing I have to say though is it's easy to write the Feynman diagrams down. It's very hard to turn the Feynman diagram, well, no, it's easy to turn the Feynman diagrams into math. It's hard to solve the math. So even though you think you might understand what's going on with Feynman diagrams, you really have a long way to go after that, because then the mathematics is very, very difficult and challenging. So, but that was one of Feynman's genius. Feynman was truly a genius, was to be able to see the linkage between these equations and these cartoons so that anyone, even I, can draw down what's going on, and then a smarter person than me can solve the mathematics, because it is very, very hard.
So, gravity is said to have an infinite range, and it travels at the speed of light. We know that some part of the universe is expanding faster than light speed. So, gravity of, say, objects here cannot affect the objects who are present in the part of universe which expands faster than light. So, gravity must have a finite range. But Einstein and Newton said that gravity has an infinite range. So were they wrong?
So it's an interesting question, and the answer is everybody's right. So let me tell you why. It is correct that there are parts of the universe that are moving away from us faster than light. And those parts of the universe are no longer able to interact with where we are now. So if you were to somehow jump outside the universe and take a photograph, objects that are more currently at this very second than 15 billion light years away are no longer, are moving away faster than light. So those objects are not connected to us in any way. So you are absolutely correct about that. Now, when Einstein and Newton say that gravity has an infinite range, well, Newton meant that the gravity would go out to infinity. And gravity sort of goes out to infinity, but he didn't have anything in his theory about an expanding universe. So his theory just was an approximation. And you know, while one might argue that 15 billion years isn't infinity, it's certainly close to infinity. It is, you know, billions of galaxies away. So to a very good approximation, Newton saying that the force due to gravity being infinite is a good one. But what you said is true, so it's not completely correct. Now with Einstein, it's a little trickier because Einstein did say that the universe was expanding. So gravity sort of has an infinite range in Einstein, but those things that are very far away, they are moving so fast that the gravity will never get to us. So, you know, now we're talking about semantics. If the force has an infinite range, but it'll never get to us, it still has an infinite range, but it also has this velocity thing that was never taken into account. So I guess you could say that the gravity, since it cannot affect things an infinite distance away, that it doesn't have an infinite range. But yet, there's nothing that just stops. It's not like 15 billion light years away, gravity turns off. It's just those galaxies move away so quickly that gravity can never catch up. And so that's an unsatisfying answer to a tricky and fun question, not one I've ever heard before, and I very much appreciate whoever asked it.
Finally, we would like to take a suggestion. What is your advice for young people who want to excel in physics?
Thank you for asking that. That's a wonderful question. So I have a couple of answers to that. And the first answer is, for every country, the rules are different. So what I'm going to tell you, I'm going to try and tell you things that are universally true, but in India, the rules are different, and I don't work in your university system, so there will be details that what I tell you may be not the most perfect answer. But in general, what I would tell you is the following. If you wish to excel in physics and eventually become a physicist, you have to go to the university for a very long time. You finish your high school, then you go to the university to get a bachelor's degree, then you must go to the university to get a PhD degree. If you do not have a PhD in physics, then you basically can't get a job. It might be unfair, but it's just the rule. A PhD is a minimum requirement to do physics research. Now, if you are going to get a job in the long term, the most important bit of evidence, or not evidence, the most important bit of advice I can give you is you should go to the most prestigious graduate school that you can get into. Now that may be different in different countries. I'm familiar with the Tata Institute of Fundamental Research in Mumbai. I've been there. There's some fascinating and intelligent people there. But that's the one university I'm very familiar with in India. Outside, there's obviously Oxford and Cambridge, which are wonderful. And in the US, we have a variety of very good schools. I'm more familiar with them being an American. You have Harvard and Princeton and Berkeley and Caltech and Stanford. These are schools that have worldwide reputations. If you go to graduate school, you should go to the best school you can get into. And the reason is because to be a physicist, you have to be smart, you have to work hard, but you actually have to know people, and you have to know powerful people, you have to know influential people. And the influential people are at these very powerful universities. So if you go there, you will make the social connections that are important. Now, that being the most important thing, the next step is, what university should you go to the best graduate schools? And here, this is better, because it doesn't matter a super bunch which undergraduate schools you go to. You should go to a good graduate school. There are many good universities in India, or if you wish, you can travel abroad. There are places in Japan or Europe or the US. But what is very important there is to, when you do your undergraduate degree, first, even if you're interested in astrophysics or particle physics or cosmology or solid state, don't worry too much about studying those things as an undergraduate. As an undergraduate, spend your time studying basic physics. Get a very good grounding in all of the basics, because that's the last time you will be able to study everything. As you get older, you'll have to focus. So you can go to any university, that whichever one is comfortable for you because you have reasons for family or whatever. You go to a good school, but my advice is, in order to get into the best graduate school, you should do some research as an undergraduate. Now, it doesn't have to be incredible research. You don't have to make a new theory of relativity or anything, but you should work with a professor who will allow you to do some creative research. Because if you do creative research, that will help you get into the good graduate schools. Of course, you still need good grades. You still have to work hard, but research is very helpful. And then finally, if you want to get into a good university, my advice as a high school student is to do very well in math. And if you can study up to calculus, that's good. You don't have to have had calculus in high school, but you should have very advanced pre-calculus, preliminary calculus, before you go to college. But if you could have calculus in high school, that's good. If you can learn to program, programming will make you useful researcher very quickly because so many calculations now are done through computer programs. I also advise that you study at least undergraduate or high school physics, preferably with calculus, but if your school doesn't have calculus, if it just has algebra physics, that's acceptable. And if you want to work at the international level, at the sort of level that I do research, it's important to have a good command of English, because when you go to the conferences, everything is in English. So you guys have no problem with that, but it's maybe difficult for people who come from other universities. I mean, other universities, other countries. So good math, good physics, and good English in high school, and programming if you can. So if you do that and then do research as an undergraduate and get into a prestigious graduate school, then that is a very good path forward to becoming a physicist. And that's my advice.
Thank you, sir, for sparing some of your valuable time.
It's been great fun. I'm very thankful that you invited me.
Thank
Good
you,
luck
sir.
to all of you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yes, sir. You're all quite welcome.